Good evening, one and all. We are discussing the third part of Unit 6 topic. So here in this video, in the third video, I'm discussing excitation circles and power circles. So and even I'm going to discuss the hunting and starting methods of synchronous motor. Yeah, first one is excitation circle diagram. So it's assumed to be one of the little bit complicated topic. Let's try to discuss the easiest, and we'll try to discuss whatever we want up to that extent only. So here excitation circle is nothing but it is the locus of armature current and the excitation voltage when lower angles are varied. So here normally we know that, let's try to discuss in the easiest manner. So we know that for a synchronous motor the equations are V equal to E plus IA into ZS. So where V is the terminal supply voltage and E is the back EMF, ZS is the IA is the armature current and ZS is the internal impedance of the synchronous machine. So from this we can able to write the equation as IA equal to V by ZS minus E by ZS. So here armature current can be obtained by with the difference of V by ZS minus E by ZS. Next, so here from the if I let me try to use the diagram so that it will be more easy for understanding. First, what I will try to do here, I will try to assume that V by ZS as in parallel to the x-axis. Okay, I'll try to assume that V by ZS is in parallel to the x-axis, which is even discussed here also. This is V by ZS. This is in parallel to x-axis. I'll try to make use of this both diagrams. Now here, with respect to V by ZS, when V and the angle between V and E is nothing but del, which is nothing but a power angle or load angle. So with respect to V in synchronous motor, E is lagging by del. When for both parameters, when ZS is divided, then even the angle will be lagging by del only. So when I'm assuming this as a V by ZS, when it is as origin and this is C, then this term is V by ZS, it is lagging by delta here, and even the other term will be it is lagging by E by ZS, it is lagging by delta here. Now I'm considering other point as OB. I'm considering the other point as OB here. Now here IA can be is equal to V by ZS minus E by ZS. So IA phasor can be obtained. These are all the phasors here. IA phasor equal to V by ZS phasor minus E by ZS phasor. So here, in order to obtain IA current here, what I'm doing here, I'm trying to draw a parallel line to this OB from the end of C here. So that too, as it is negative sign here, I'm trying to draw in the opposite direction. So it is more clear here. So to this OB with the same length, I'm drawing a parallel line to the opposite line. So this value is equal to the minus E by ZS here. So from this, we already discussed that IA equal to V by ZS minus E by ZS. Here, the phasor difference between V by ZS minus E by ZS will be equal to IA. So this current OA is the IA current. Even we can use this parallelogram method, and we can use that A square under so between two phasors, if I want to find out that A square plus B under root of A square plus B square plus 2AB into cos of theta by 2, even with this also we can able to get the same formula and extension. So I'm trying to directly explain you the conclusion here. This is the OA phasor is the IA current. It's obtained by the phasor difference of V by ZS minus E by ZS here. Now here in the diagram, it is assumed V by Z is assumed as horizontal in such a way that V phasor is drawn somewhere. Now here from this, as this is IA phasor here, with the angle between IA and V is nothing but phase angle phi. Now here with the known value of phi, so I'll try to find out the VT phasor. So from IA phasor, I'm trying to with an angle of phi, I can able to find out the VT phasor. Now here we know the angle between VT and E, VF and VT and EF, that is nothing but delta here. So with respect to VT, I can also even find out the EF. In this manner, I can able to find out OB, OC, IA, and V and EF. So this is what we discussed up to this extent here. For when V is assumed to be constant, for a constant field excitation, when the extremities of the phasors E by ZS and IA follows the path of circle, the load angle varies. This is known as excitation circles. So let me try to explain in short here. So when we assume that when E is greater than V condition, at that time, we need to assume that the phasors of E by ZS, the phasor of E by ZS and IA has to be maximum here. Now here from this point, what I'm doing here, so this E by ZS and IA both are in additive nature, so that maximum point will be considered as the radius. So this total length will be considered as the radius. This happens only when E is greater than V here. So we assume C as a center and draw a circle here. This circle is nothing but power circle when E is greater than V here. Even you can able to see this. This is the center when condition when E is greater than V here. Next, this OF is the phasor. Okay, and the same armature current value is equal to OF here. When E is less than V here, at that time, so to this E by ZS phasor, the IA phasor will be drawn opposite here. So that the value will from this end, the IA phasor will be drawn opposite. From this, the circle radius will be decreases. Okay, it is opposite to the actual case here. So circle radius will decreases here. In this manner, we can able to, by considering this reduced length, we have to draw the semicircle. In this manner, we can able to find out the reduced semicircle here. So the same we can able to observe. This one condition is E greater than V, another condition is E less than V here. So this is the total excitation circle diagram for a synchronous motor, and I hope this is sufficient for our explanation and for exam point of view and for our content. Next, we will try to discuss the power circle. Power circle gives us the locus of armature current IA and mechanical power developed and power factor angle when varied here. So here small derivations are there. So we know this for synchronous motor, input power equal to mechanical power plus losses here. So input power can be considered as V into IA into cos phi. Mechanical power is PM and losses is nothing but IA square into RA. From this, I can able to find out, I can able to write down in terms of IA square into RA minus VA into cos phi plus EM equal to 0. So here I'm shifting this RA to the other parameters so that the equation will be simplified like this. So as we know that sin square theta plus cos square theta equal to 1, I'm adding this term here so that the equation will be IA square cos phi plus IA square sin phi, and rest of the term is same. Okay. So if I assume that x equal to IA cos sin phi and y equal to IA cos phi, we'll get an equation like this: x square plus y square minus v by 2 RA y plus this equation. So this is in terms of the equation of a circle here. So where if I assume that x square plus y square plus 2gx plus 2fy plus c equal to 0, with the equation like this, then the center of the circle will be minus g and minus f. As we don't have any x term here, so the minus g will be 0 here, and as we have y term here, is this v by 2 RA will be the y term here. The center will be obtained here 0 comma 2 by v by 2 RA, and with the radius will be the formula is we have again the formula here. Radius equal to 0 g square plus f square minus c. So here as we don't have any g term here, f square equal to v by 2 RA minus c equal to pm by 2 RA. From this we can able to get this equation here. So we are rewriting the above equation in terms of equation of circle, and we are going to find out the circle and center and radius. So next, so yeah, the circle diagram is shown in the figure, and here coordinates equal to OE here, OA equal to radius equal to IA here. So this is V equal to V by 2FA to RA, and this is the center, and radius equal to, that is equal to OA, radius equal to IA here. How we are going to see this? So now after drawing a circle, the line after drawing the circle from O, and if I draw any tangent here from O, if I draw a line such that it touches the circle, then that point will be IA here. That point will be IA, and this point, this is equal to V. This is the radius of the circle, which we already discussed, that V square by 2 area minus PM by RA here. Okay, minus PM by RA. I'm using the both diagrams here. If I assume the case one, when the machine is on no load, when the machine is completely under the no load condition, at that time the mechanical power will be developed 0 here. So here the mechanical power equation. So here the mechanical power equation is equal to, we have the formula here. The radius of the formula equal to minus v by 2 RA minus PA minus PM minus all square minus equal to 0 here. When mechanical power is 0, at that time we need to equate it to 0 here. So in this case, this is the radius of the circle. We already discussed the condition here. This is the radius of the circle. When mechanical power is 0, this total term will be 0, and the radius will be equal to v under root of v by 2 RA whole square. So that's the radius will be equal to v by 2 RA. So I can get a condition that when under no load condition, the radius will be equal to v by 2 RA. That is what we represented. That is what we represented even in the diagram. That is what we represented even in the diagram. Yeah. So the radius will be v by 2 RA. This is the maximum condition when under the no load condition. And here the mechanical force is 0, and circle passes through the origin. Under this condition, the circle is passing through the origin here. Case 2, when machine is under full load condition. In machine is full load condition, all the power is the maximum mechanical power is generated, and when the this term is maximum value, and total value will be 0 here. When this term is becoming 0, the radius will be becoming the radius of the circle will be 0. For the full load condition, the radius will be 0, and for no load condition, the radius will be v by 2 RA. To get maximum power condition, if I equate, I will get a P max equal to v square by 4 RA condition, p square by 4 RA condition, and we can able to extend this concept by what is the efficiency of the condition here. That is, by simplifying that, we can able to get that efficiency equal to 50% of this. So this is the power circle. I hope it's clear. Yes. So next, hunting and suppression of hunting, and we have discussed so many times in detail about this hunting and suppression of hunting. Hunting is nothing but when momentary fluctuations and when due to some external disturbances occurs in the machine. At that time, the rotor falls back with respect to the stator flux, and it's try to follows the stator flux here. So we even considered the same example even when while discussing about the synchronous generators also. I hope there is no need to discuss in depth. So this is this the angle between the stator poles and rotor poles is nothing but the coupling angle. Coupling angle is represented with an alpha. So stator poles, the angle between the stator poles and rotor poles, we see that the coupling angle should be 0. But when hunting occurs here, when rotor pulls back, then this coupling angle will be not equal to 0. It will keep on it will be somewhere 10 to 15 degrees. We should see to that the coupling angle should not cross a certain limit. So if not, the machine will become unstable, and the rotor completely falls back. And here on how to overcome this. So in order to overcome this, we need to use the damper bars. We need to use the damper bars. The damper bars we already discussed. These damper bars are short circuited copper bars which are placed on both sides of the end rings. So with this, even the machine is rotating with the lower speed or more than the higher speed. So damper bar see to that it will try to regulate the machine speed to the back to the synchronous speed. That is the purpose of the damper bar. So here the damper bars will act only when the machine is under the disturbance, when the machine speed is not equal to the synchronous speed. When I think when the machine is running at the lower speed, at that time extra mechanical energy is given from the damper bars, and when machine is running with the over speed, external extra mechanical energy is converted to the electrical energy. So in this manner, induction generator and induction motor action takes place in the damper bars here, and this process is hunting is nothing but what is the problem and how we are going to suppress the hunting by using the damper bars. So next one is starting methods of synchronous motor. So here, as we already discussed, that synchronous motors is not a self-starting motor. So we use certain external methods to start the synchronous motor. I hope we discussed this in short without just random in rough. We discuss these topics. We will try to discuss in detail about this. So there are we normally use four methods to for starting methods. That is using the pony motors, using the DC motors, using the spring induction motor, and damper bars. So first one is pony motor method or induction method. Pony motor method. Pony motor method. These are the small induction motors where the rotor poles is number of rotor poles is less than the pony motor rotor poles equal to less 2 number is equal to synchronous motor poles minus 2 here. So this is the relation which I remember. So we need to cross check this. And here when this pony motor with small motors with induction motor, when these are connected to the synchronous motor, so this will make the rotor to rotate near to the synchronous speed. In any case, we need to see this. The rotor of the synchronous motor is brought near to the synchronous speed, then excitation is to be given to the synchronous motor, so that with the given excitation, the rotor which is rotating near to the synchronous speed will be pulled into the synchronism by the synchronous machine with the DC with the given excitation. Similarly, in this also, so by using this pony motor, we'll try to make the rotor of the synchronous machine to rotate near to the synchronous speed. And after that, the DC excitation is given to the rotor, and once the DC excitation is given, the DC supply, the excitation which pulls the rotor into the synchronous speed, so that the coupling angle exists between the rotor poles and stator poles, which makes the rotor to rotate continuously with the synchronous speed. Once the machine is brought to the synchronous speed, the pony motor is disconnected. Okay. The pony motor is disconnected from the supply here. So this is the corresponding diagram of a For a synchronous motor, the pony motor is connected. This is a random diagram which is connected. Second one is using the small DC machine. Here, I'm using the DC machine as a prime mover or mechanical energy device for the synchronous, for the starting of synchronous machine. Here, in this case, the DC machine. So here, it is mostly used in the large synchronous motors. So here, DC machine is connected. The DC motor which generates which takes electrical energy and gives a mechanical energy. Here, the DC machine is used as a DC motor. Initially, it is used as a DC motor, and it will try to make the it will try to deliver the mechanical energy to the synchronous motor. It will try to make the rotor of a synchronous machine near to the synchronous speed. When the machine is brought near to synchronous speed, now again the same DC machine is used as DC generator, and it supplies the DC excitation to the rotor of a synchronous motor. So up to the synchronous speed, up to first in first case, the DC machine is used as a DC motor, and it will try to make the synchronous machine bring near to the synchronous speed. Once the speed of the synchronous machine is brought near to the synchronous speed, again the same DC machine is used as a DC generator, which can be used to supply the DC excitation of synchronous rotor. Once the DC excitation is given, the rotor again pulled by the stator fields, and it will try to rotate the synchronous speed here. This is by using the DC machine. So in this case, DC machine can be used in the both cases here. It can be used as a DC motor as well as DC generator, and it has an advantage like low power usage and the easy starting. And using the damper bindings, we have discussed so many times about the damper bars here. So let me try to explain in short. In first, synchronous motor acts as induction motor. So here there is no starting. Here damper bars itself is used as a starting method. So initially, due to the presence of this damper bars, it acts as an induction motor. So induction motor, and we will try to bring machine into the subsynchronous speed. Then from zero speed to the near to the synchronous speed, due to the presence of this damping torque or damper bars, the induction motor torque is developed, which converts electrical energy into mechanical energy, which will try to make this induction rotor of a synchronous machine near to the synchronous speed. When the DC exit, then at this instant, DC supply is given to the rotor of the field winding. Then due to that, when the DC supply is given, the motor gets pulled into the synchronism and starts rotating at synchronous speed. The concept is same, but we are using different methods here: damper bars, the DC machine, and pony motor. And last one is slip-ring induction motor. So this is one of the type of the slip-ring induction motor. We have two types: squirrel cage induction motor, and another one is slip-ring induction motor. In squirrel cage induction motor, there is no facility of adding the external resistance, whereas in slip-ring induction motor, the external resistance can be added here. So we'll try to make use of this, adding the external resistance here. In this method, an external rheostat can be introduced here, and we know that we have one more formula: starting torque is proportional to the RST. That is, if the rotor external resistance is increased, the starting torque can be improved here. We'll try to make use of this advantage. So initially, we'll try to keep the rotor external resistance at the maximum value, so that maximum torque is generated, and so that the machine starts rotating. Here I'm using this slip-ring induction motor as a prime mover, which can be connected to the synchronous machine. So with this by increasing by keeping the maximum value of external resistance, the maximum torque will be generated. The same can be applied to the rotor. So the machine is made to rotate near to the synchronous speed. Once the machine is brought near to the synchronous speed, the DC excitation is given to the rotor. Then motor gets pulled into the synchronism and starts rotating at synchronous speed. And once the machine is brought to the synchronous speed, again we'll try to disconnect the external resistance, and we'll try to disconnect the machine also. So in this manner, we can able to see to that the starting of a synchronous motor can be done by all these methods. So this concludes different starting methods of synchronous machine, and hunting, and excitation circuits and power circuits. I hope that it's a little bit boring to stay in the home, even for you people as well as for me. I hope that due to the present scenario which we never faced, it's equally important to stay and protect ourselves as well as our family members by staying at home. Okay, keep enjoying and keep stay home. This is the time this is the opportunity where we can spend our maximum time with our parents. Okay, so that's all for today's, and this concludes the Unit 6 topic. Thank you.